researchers meet at QIQT. So this is the morning session. So
we
the
cannot see
morning,
your face video. Is it you don't have a?
I have 1 second. Yeah,
Yeah, it's okay.
okay. So welcome to the morning session of researchers meet at QIQT. So in morning session, there will be, I think, 6 talks. So each talk will have 30 minutes to 20 minutes for presentation and 10 minutes for discussion. So the first talk will be given by Nitish Kumar Chandra. He is doing PhD from University of Pittsburgh, Pennsylvania. So I have known Nitish for I think 4 years when he was at ISER and I was as a research associate there. So he is one of the good researcher. So Nitish, you can share your slide and start.
Thank you, Dr. Radhya. Yeah. Am I audible?
Yeah, you are ready.
Okay. Yeah. Just let me know like if you can see my screen.
Yes, it is visible. Please make it full screen.
Yes. So just a second.
Yes, it is full screen now.
Yes. Okay. So
go
is
ahead.
my voice okay?
Yeah. Okay.
Okay. First of all, thank you to Professor Panigai for organizing this QIQT23. So I'm a PhD student here at School of Computing and Information, University of Pittsburgh. So I'll be talking about the works which have been going here in our group. This is about quantum switches in a quantum network. More precisely, I'll talk about a policy which we have figured out using Markov decision process. And my talk is titled Optimizing Quantum Distillation with Quantum Switches in a Quantum Network. So I'll like briefly talk about like what are quantum networks, and then I'll talk about the components of quantum networks. So quantum switch is one of the most important component. And then we figured a policy for quantum switch based on a decision process. And then I'll talk about results and what's the ongoing work and what's the future direction that we can hope to see in this field. So this is the recent work, we put it in archive. So this is titled Optimal Entanglement Distillation Policies for Quantum Switches. So what is a quantum network? Mathematically speaking, it can be considered as a graph. So a graph has vertices and edges. So here vertices correspond to the senders and receivers, and the edges correspond to the elementary links. So what are elementary links? So elementary links can be shared bell pairs. So if we see like the red lines, they are the bell pairs shared between the two end nodes, and the blue bubbles correspond to case where we have a k-partite elementary link. So for example, a GHG state is shared between three parties. So what's the goal of quantum network? The goal is to connect different nodes which are present in the graph. So this has to be through a optimal protocol, which we need to figure out. So given a set of elementary links, we need to figure out a protocol so that we can connect the end nodes. So this will require a couple of things, such as like a pathfinding algorithm, and also certain things which I'll talk about. Between two elementary links, it can have between two nodes, it can have one or more elementary links. So once elementary link is generated, it is stored in quantum memories. So each node has some memories and they can store the elementary links. But a real quantum system would decoher with time, that we have considered in our work. So how this elementary link is generated? So there is a source. The nodes basically request the source to send elementary links, and that is how we are able to get elementary links between the two parties, further entanglement swap operation is done so that to connect the two end nodes. But as of now, we don't have full-fledged quantum computers. So we restrict ourselves to something called near-term quantum networks, a term widely used in the recent literature. So what is this near-term quantum networks? So we can only deal with small number of nodes, and also the entanglement source that we have is imperfect. So even though we try to generate maximally entangled state, but we may not be able to generate it every time. And also to connect end nodes to make virtual links, we need to perform entanglement swap operation. Though entanglement swap operation can be done deterministically, but noise do occur, and it may become probabilistic. And the measurement that we perform is also imperfect. So in future, we may need to do quantum error correction, but as of now, we don't have the capacity to do full-fledged error correction. And as we know that the qubits that we have coherence time, so that also needs to be considered. And even we don't have the capacity to do entanglement distillation. So like a NK distillation policy, uh, where N and K are large, is like very difficult to perform. So we restrict ourselves to something called 2-to-1 distillation Bennett protocol that we have done in our work. So to summarize, like what are near-term quantum networks? So we start with a physical graph. We are able to generate elementary links as the nodes request from the source. And then via some protocol, we are able to generate virtual links, which connects the distant nodes. So how can that be done? That is done through performing some joint measurement, like entanglement swapping. And also we need to figure out best optimal way to do that. For that, we may require some pathfinding algorithms. But still we have certain more issues, such as we need to figure out the optimal rate at which we can do entanglement generation. Since coherence time is limited, we also need to factor in that. And we need to know the exact policy. The challenges we face is that the link generation is probabilistic, and also the elementary links decoher with time. So what is a full-fledged quantum network? So though I discussed near-term quantum networks, but in future, we hope to achieve full-fledged quantum networks. So in that, the end nodes will be more sophisticated. It will be able to store qubits. It will be able to perform gates and do measurements. And also it may be able to do fault tolerance and error correction. So what are these quantities? So these are repeaters. Repeaters are basically so the quantum signals that we have that may decay with time. So to boost that signal, we use something called quantum repeaters, which I will talk in a bit. And then we have something called quantum switches. The role of a quantum switch is to basically connect the end nodes, and also it is more sophisticated in terms that it can decide a switching policy, and can find an optimal way to connect the end nodes. So what are quantum repeaters? So as I said that the quantum signals decay with time, we need to boost them. So that can be done through quantum repeaters. So how does it do it? So what it does is it first generate entanglement, like which can be seen from the dashed line, and then at like each node, and then it performs joint measurement, which is called entanglement swap operation. So it will first share the bell pair and then perform a joint measurement so that it will connect the end nodes. This is the role of a quantum repeater. So what is a quantum switch? So a quantum switch is first a quantum repeater, but it is more sophisticated as it can handle multiple users. It can direct entanglement flow through different paths in a network. So what it does is it first establishes individual elementary links with the clients, and then it performs a joint measurement to connect the end-to-end node, which is called end-to-end entanglement. So it can so the switch can act according to a switching policy. So it knows it can select a set of clients and also apply a certain threshold on the end-to-end entanglement links, which I'll talk about. So basically, to summarize, a quantum switch is a quantum repeater, but it has additional advantage that it can route entanglement through multiple users. So this is the switch that we have considered in our work. So let's talk about this switch. So what this switch is about is that it has elementary links. So what it does is each client tries to connect with the quantum switch. And this process is probabilistic. So it will try to it will try to generate elementary links after a certain time interval. And then also we can see that these are like thick lines and then there are thin lines. So implying that it is decohering with time. So once we have sufficient elementary links, what switch can do is it can perform the joint measurement on any of this link, and any of this link end up connecting user A and user B. But here we have limited ourselves to certain conditions, such as we have finite storage. So it's so the switch can only store certain amount of link. It's the symmetric in both case. So each user tries to make elementary links, and quantum switch, what it does is it performs joint measurement and then connect end to end to generate end to end links. But here what we have considered in our work is something called quantum distillation, which I'll talk about. So what is quantum distillation? So quantum distillation is a protocol which basically takes in multiple elementary links and then gives us one elementary link. So at the cost of more weak elementary links, it gives us a better elementary link. So, and we wanted to study that. So how does quantum distillation helps us in, say, finding better end-to-end throughput. So what is throughput? End-to-end throughput is basically if we consider after a time interval, how many end-to-end links we have been able to generate. And here, like these black dots are quantum memories, and these are the elementary links. So as I said that we have considered quantum distillation protocol called Bennett protocol. So let's talk about this Bennett protocol. So this Bennett protocol is basically 2-to-1 distillation policy in which you consider two elementary links, you perform C0 operations, and then do measurement. So if you get same result, basically the protocol has succeeded and you end up having a better link. So this process is heralded. So we know like when the distillation has happened and when it has failed. As I told earlier, like how our quantum switch is modeled. So what happens is each user tries to generate bell pairs, and the quantum switch can do three things. First, it can do nothing. Basically, it can wait for more and more elementary links to come up, or it can do quantum distillation. So it can basically take in two elementary links and give us one better link which has higher fidelity, or it can do entanglement swap, basically connecting end-to-end entanglement links. So here we have considered Markov decision process to find the optimal policy for distributing end-to-end bell pairs by randomly generating bell pairs having two users. So we have restricted ourselves to two user, and the switch can so we have considered two policies, one policy in which we allow distillation to happen, and in other policy it can only swap. And we see that there is a marked difference, and basically we have advantage when we use quantum distillation as one of the actions that is allowed. And also we have considered that the end-to-end link should have certain fidelity threshold. So basically the users can demand that that we need to have a certain fidelity threshold for our end-to-end links that we have considered. So let's see what is a Markov decision process. So a Markov decision process is a stochastic process which basically describes a framework for sequential decision making. So what it does is it basically tries to optimize a reward metric. So what is a reward environment? What this does is this basically makes a transition. So from the state ST, the agents applies some action on the environment, and that ends up giving us a new reward and a new state. And this process is repeated. So but at the end of the process, we have a certain reward, and that is in our control. So to optimize end-to-end throughput, we can define a reward function such that MDP will try to maximize it, and in turn give us the policy for maximizing end-to-end throughput that we have considered in our work. So like there are certain components of MDP. So for to define MDP, we need to define something called quantum states, and then we need to define actions, and then also we need to get the transition probability matrix. So what are the states that needs to be defined, and that I'll talk in a bit. So these like are the three components: the state, the action, and the probability transition matrix. We have another thing called reward, which I talked about. So how have we defined our MDP? So we have defined our MDP by using by defining age vector. So what is this age vector? This age vector is basically quantity which describes how old are the elementary links that have been generated randomly. And the switch, as I told earlier, can do three things to the elementary links. It can do nothing. So in that case, it will wait for one time step so that more and more elementary links are generated. Or it can, so if there are two elementary links available on either side, it can do an entanglement swap operation, or it can basically do elementary quantum distillation of two elementary links to get one elementary link of higher fidelity. But like, so defining full-fledged Markov decision process is quite difficult. So we needed to make some assumptions. So we made some assumptions like the probability of success of entanglement swap is 1. This was based on a simple fact that when we do Bell measurements locally on a, say, a matter-based quantum memory like a trapped ion or an NV center in nitrogen diamond, then it can succeed with a unique probability. So we have restricted ourselves to 2 users, and they have identical link generation probability. And we have considered star topology. And we have considered that quantum switch has a certain memory, so it can store only up to L number of elementary links for each client. And also we have assumed that in unit time step, the probabilistic link generation has happened. And also in the same time step, the switch applies one action. So if we move to next time step, we have done basically 2 things. We have initially we had probabilistic link generation, and also one action has been taken by the switch by the end of one time step. And also to make our state space tractable, we considered only discrete set of states. So we considered that the fidelity is having exponential decay, and defined as, say, e to the power minus alpha m, and we have considered only discrete time step that m varies as 1, 2, 3, 4. And also we have considered till a certain time. So for example, a Warner state is entangled only till its fidelity is 0.5. After that, it becomes separable. So, and also to simplify a state space, we have considered discrete time step, and also that the fidelities are discrete, as in like for each time step, it's not continuous, but we have certain fixed values of the state. So how have we find the optimal policy? So what is an optimal policy? So an optimal policy is a decision-making process which guides the course of action. So basically what it does is it maps, so you give me a state, and this, according to this policy, I have to apply some action. So it basically maps the state to a set of actions, but a deterministic policy maps one state to a particular action that we have considered here. So what we did was we considered Markov decision process for one we have found using this Markov decision process, one policy using Markov decision process, and in the other heuristic, we considered an policy in which we don't apply quantum distillation. So in that case, it has only two possibilities, whether to wait or to do end-to-end swap, so that to get the end-to-end link. So we then simulated our results. So our goal was to maximize throughput. Throughput is defined as the number of end-to-end links. So we repeated the simulation for 10,000 steps, and we varied our fidelity from 0.7 to 0.95. So this fidelity is the end-to-end fidelity of the link. So, and then here I have shown two quantities. One is average throughput, and another is average fidelity of the elementary links. So this is our result. So the blue line is about policy in which we allow distillation, which is, and in the other one is distillation is not allowed. So we see that initially we don't have any advantage, but as time progresses, we are able to see certain advantage here and also here. So what is this? So this tells us that as you move to fidelity threshold of the end-to-end link, which is quite high, then if you don't allow entanglement distillation, you won't have advantage. So you need to have a policy in which you allow distillation so as to get the advantage. So how is this advantage happening? So what distillation does is it basically takes two links and then gives us one link. So what it does is, so even though our ages might have decayed, but the policy is defined as such that it takes into two links and gives us a better link. So that is why we are able to maximize the average throughput by using a policy in which we allow distillation. So we did our simulation for the age, which was 3, and then the storage capacity was 3. So the switch can store only 3 links for client A and for client B. So this is the plot for average fidelity. So since we have defined a reward function to maximize end-to-end throughput, we won't see any advantage in fidelity. This is because here what happens is when the goal is to get maximum end-to-end links, the policy will not bother whether you give it a link as long as it crosses the fidelity threshold.
Nitish, you have 5 more minutes, okay?
Okay. Yeah, I'm almost done. So, so to summarize, we have considered a 2-to-1 distillation policy in our entanglement switch, but in future we can basically do a more complicated protocol, such as we may take a higher value of n that will transform to lower values of elementary links. So we have considered only 2 clients, but this can be increased, and also we can have a more fine-grained state space. In future, the goal is to do for a continuous state space, but that is quite complicated as of now. So what's the current status? The current status is we only have commercial systems for quantum key distribution on the market, but we don't have a full-fledged quantum network. Because like we don't have proper quantum repeaters and quantum switches as of now, which can do error correction. Like in future, we need to have quantum repeaters which have improved rate of photonic qubit transfer, and also we'll need 2 types of channel. One is free space channel, and other is fiber based channels. Both has their own advantage and disadvantage, but a future quantum internet will require both of them. And also we'll need to have develop policies such that we will able to mitigate qubit lifetimes, as we know that qubits have limited coherence time. Though it seems hard to predict till when we will have a full-fledged quantum internet, but we do see that some work have started in this field, and we do hope to get it in like next few years. Thank you. So
Okay, thank you, Nitish, for the beautiful talk. So the floor is now out, open for the questions.
Yes.
Can I ask questions?
Yeah, please.
Yeah, please do.
Thank you for your talk.
Yes.
What is the definition of decoherence time? Could you please?
Okay. So the way decoherence is defined as, since we have considered an exponential decay, we have modeled our fidelity as e to the power minus alpha m. Alpha is some constant, and m tells us basically the age in which, so for example, if we consider, say that we want to decay our state in 3 time steps, then say e to the power minus alpha m star will be 0.5. We have we take 0.5 because for Wagner states, this is the point at which the states become separable from entangled. And decoherence in general is a phenomenon in which the states decay. So even if you start with Bell pairs, you end up having a mixed state, though you have started from a pure entangled state.
Thank you. What type of decoherence mechanism you considered when you talked about decoherence time?
So we didn't consider any particular, but one such process can be depolarizing channels. So what you do is you apply depolarizing channels at the end of Wagner states. So a Wagner state, we have considered a 2-qubit Wagner state. So you take both the qubits, and in each qubit individually apply a depolarizing channel. So what's a depolarizing channel? A depolarizing channel is you take the state with p probability and retain it with p probability, but with some 1 minus p probability, you transform it to a maximally mixed state I/2, which has basically 0 coherence. And if you consider that and then calculate the fidelity, you can end up having a exponential decay type of fidelity.
Thank you.
Is there any other question?
I have a small question. So you have, this is an experimental work. You have done experimentally you have done.
This is entirely simulation work.
Entirely simulation. I see.
Yes.
Okay. Nice idea, actually. Very nice idea. Yeah.
Yes.
Thanks.
Thank you.
Okay, we have a few minutes for some questions also.
Can I ask one more question? Sorry.
Yeah,
yes,
please.
Could you please explain why you consider Werner states? Any reasons?
So a Wagner state is like a best case scenario in which you have, in real situation, if you take Bell pairs and if you let it decay, it ends up becoming a Wagner state. And it has been experimentally observed. So even in like optical photonic systems, we end up having Wagner states.
Can we consider known states and maybe other ones? And then
I mean, known state, I think is a sort of highly entangled state, and it doesn't have any parameter as such, but a Warner state is like a parameter which you can vary and then get from a less entangled state to a more entangled state. Known state is a fixed state, like a GHG state, and like it is used in quantum metrology. And in that, if you do that, you get like you can achieve the Heisenberg limit and other limits. You can basically cross the standard quantum limit that we observe. And like basically, if you do quantum sensing, you will be able to reach the CF, like the Fisher information, quantum Fisher information.
Clear. Thank you.
Okay, Nitish, you have mentioned about star topology. What is it?
So star topology is basically you consider a switch and the clients are located like nearby. So you basically end up having a star type of thing. So it doesn't have like a physical meaning, but just like the topology we consider is similar to a star. That's it.
Okay.
So we have considered two, but if you consider say a K clients, then it will become like a center and then a K lines around it. That's it.
Okay, so let us thank Nitish once again. So thank you very much for giving this talk. So the next
Thank you,
talk